10.2 and 10.3. Oops. Parametric equations. Oops. Alright guys, so today we're going to be going over parametric equations, which is 10.2 and 10.3 in the textbook. Alright, let's get started. So first, we're going to, let's go over what parametric equations are. So, let's see if f and g, can't spell, if f and g are continuous functions of t, so f of t and g of t, they're continuous functions of t on an interval I, then the equations x equals f of t and y equals g of t are parametric equations, and t is the parameter. So together, these parametric equations and the graphs that they form are called a plane curve. So you might be thinking, why do we care about parametric equations? Well, parametric equations can be used to represent functions that, well, by definition, aren't functions, such as something that might look like this. And by our vertical line rule, we can see this is not a function. So parametric equations are good for that. So yeah, let's dive into some problems. First let's cover the derivative. So derivative of parametric equations, if you have the two curves, x equals f of t, y equals g of t, then the slope, or the derivative, is dy over dx equals the dy over dt. So derivative of y with respect to t over derivative of x with respect to t. And this cannot equal 0. The second derivative is going to be you're taking the original derivative with respect to t all over dx dt, and so on. So if you just do the same thing for the third derivative and the fourth derivative, so you get the point. Alright, so let's I kind of skipped over eliminating the parameter because that's pretty easy stuff. You just plug in the equivalent equations, r equals, or solve for t, sorry, not r, I'm thinking about polar right now. Solve for t and plug into the other equations, pretty straightforward. But let's do a problem about derivatives. So we're going to be doing problem number 2 in 10.3, and the problem asks to find the derivative of the third root, x equals the third root of t, and y equals 4 minus t. Right? Yeah. Okay, so let's see, 10.2. So basically what we do is we take a derivative of y with respect to t, so that's -1 over, and then we take the derivative of x with respect to t, so it's 1/3 t to the -2/3, and this will equal -3 t to the 2/3. Now if we want to take the second derivative, what we do is we take derivative with respect to t of this, so that would be -2 t to the -1/3 all over derivative of x with respect to t, which is still 1/3 t to the negative 2/3. So what this would be is t to the 1/3 negative 6t to the 1/3. Yeah. Oh, sorry if you guys can't see that. It might be off my recording screen. But the answer should be 6t to the 1/3 if you're looking for the second derivative. All right. Now let's quickly go over arc length. So arc length of parametric equations would be in the form of s equals the integral from a to b. So you've seen this before when we were doing normal surface area. A to b of the derivative of x with respect to t squared plus derivative of y with respect to t squared dt. So it's very simple stuff, almost just plug in questions. Let's do an example. Let's do number 46 in 10.3. So basically, it's just a pretty basic integration problem. We're trying to find the arc length of the curve x equals 6t squared, y equals 2t cubed from 1 to 4. So we set our integral 1 to 4, and the derivative of x is 12t, so we square that, plus the derivative of y is 6t squared, and we square that, dt. Now, so you just basically simplify it, 1 to 4, you can get it into the form of 6t squared of t squared plus 4. Now it's just a u sub, u equals t squared plus 4, du equals 2t dt. You have to change the limits of integration, so u of 1 equals 5, u of 4 equals 20. And let's clear the screen real quick. We have more room. And once you do the u sub, you come out with 70 root 5. All right, pretty simple.